Today we're going to continue our discussion of ward identities and focus and specialize the things we've discovered so far to the case of 2 plus 0 dimensions. And then we're going to connect this discussion with this procedure known as radial quantization. And this will be in preparation for the final lectures where we will present an example of a quantum theory that's a conformal field theory, and also understand the algebra generated by the symmetry generators of conformal transformations. So just to bring us up to speed, I'll mention a couple of words about ward identities and why we are focusing on them. Just to summarize the progress so far. So what we're looking at is some quantum theory so we have some Hilbert space H for our quantum theory, and we have some set of observables for our quantum theory. Call it calligraphic O, which some collection of linear operators on Hilbert space. Positive. We could make them positive, but we won't really need to worry about that distinction in this course. So that's a quantum theory. A quantum theory is a configuration space and a collection of observables. Now it becomes more like a field theory if there's a subset of observables, which you might call fields, which have a label attached to them. Maybe we call that subset of observables F, and an observable inside F has a label referring to space-time location and possibly some other spin label or tensor label or just some other collection of labels. Has labels X, alpha. So you could subscript these special observables with X and alpha. Now, we don't get to call this quantum field theory unless there's some symmetries that act on this set of observables. So we get a quantum field theory, say a Minkowski quantum field theory or a Euclidean quantum field theory, when the symmetries act on our observables. Now, properly we should take the symmetries to act on all the observables of the theory, but typically we just focus on the action of symmetries on a handful of special observables that we call fields. Now, let's consider the example of translation invariance. That's a symmetry of many theories. How does that act on our observables? Well, if you have an observable initially at some space-time location x, then you translate it a bit. You look at the system relative to a different location, x minus epsilon. Then we know how this symmetry should act. It should just translate the argument there. Now, this thing here is a nasty, it's not clear what this thing is here mathematically. This is a distribution valued operator in general, mathematically pretty poorly defined. So we usually say that such things don't make sense independent of an expectation value. So you need an expectation value to give some sense to this thing here. So these things are taken really to only make sense inside expectation values like this. But once you do that, then you get some perfectly ordinary, if your theory is not completely sick, you should get a reasonable function just of x plus epsilon, the spin label, and of course these in and out states, A and B. Should be a perfectly respectable function f. Now, there's two ways of having our symmetry act in this context here. So one way is you just look at this and you say, well, I know what to do with a function of an argument. I just Taylor expand it. Take this function, whatever it is, it's meant to be a nice function. So how do you evaluate this function under a small symmetry transformation? Well, it's just the function. Plus, and let's suppose we're doing small transformations. We're going to focus our attention on infinitesimal symmetry transformations, make our life a bit easier. And then we just Taylor expand in the smallness of this epsilon here. So you get a first order term. And you get some second order terms, third order terms, and so on. So a symmetry translation acts to first order as f of x alpha b a b goes to f of x alpha a b plus epsilon, the first derivative of f. That's what it means, translation invariance. Now this should be true for all nice A and B. So we have this expression, and it shouldn't really matter what happened in the past and what happens in the future, as long as what's happening in the past and the future doesn't create black holes or something. Then this expression should be true for all sufficiently nice A and B. So then the way we express that notationally is pretty poor, pretty bad notation, what we're about to do, but this is standard. We express it by just taking off the A and the B. So this is, as written here, this is not in general, healthy expression, because these things here are like delta functions, but delta functions whose values are operators, not functions, not numbers. So they are. It's a hazardous expression at the best of times, right? To have a delta function is equal to a delta function. One argument is equal to a delta function, and another plus epsilon, the derivative of the delta function. Turns out it works for delta functions actually. So it's a hazardous expression. It has to be interpreted with caution. And whenever you see a naked expression like this without expectation value, you have to immediately substitute the condition that this is only to be interpreted with respect to inner products or expectation values against sufficiently nice input and output states. So whenever I write any time in this course something that has bare field operators or anything like that, then actually I'm not saying that this is equal as an operator expression. I'm saying this is equal only up to evaluation in inner products like that. So translation invariance, we can say, well, okay, that's how translation invariance acts. Now, similarly, I mean, or not even similarly, right? Translation invariance includes time translation invariance. Just put a dot there. Suppose we have a 4-vector. This epsilon is epsilon in the first argument, but 0 in the others. That means we're not translating in space, just in time. So then, making a translation in time is the same as doing this inside correlation functions. So that's one way. I mean, this is completely given by the data that we have. So we know that's just what it means, time translation invariance or spatial translation invariance. But we have a whole other way of doing these symmetry operations in quantum theory. Since these symmetries are symmetries, they should act they're going to act as unitaries on our underlying Hilbert space. So in the case of translations, there's some u that depends on this epsilon vector, which is telling us where we're translating. And that's going to be minus I epsilon dot p hat. P is the energy momentum 4 vector. And P are a bunch of operators. And they're not easy to discover, these operators. When you build a quantum theory, you typically work out correlation functions. And it's not, when you quantize a field theory, it's not immediately obvious what H, P, X, Y, and Z are. You have to work quite hard in canonical quantization write down sensible expressions for these things. So there is, using the fact that our symmetries are acting like this, we have a whole other expression for translation invariance. An equivalent expression even. So in the Heisenberg picture, a symmetry acts like this. And then if we just recklessly Taylor expand that expression here, then we'll get a expression. Plus I. So there we go. We've got two ways to carry out this symmetry transformation. And the Ward identity just connects these two ways of doing these symmetry transformations. And if you employ the path integral, it gives you a way to discover what is the correct generators. So I've already said the Ward identity in words, right? Since these symmetries act as unitaries, it should be that phi at x plus epsilon comma alpha should be equal to, well, this, that's what it means to be translated. And also there should be a unitary transformation which does that translation. So these two things should be the same, but only inside correlation functions. And that's what a Ward identity tells us. These things are the same. And then also via the path integral, yeah, a question?
I'm sorry, but don't you have to add the epsilon in the left-hand side on your right-hand side formula? Because
oh gosh, sorry. Yeah, the question is, shouldn't I have an epsilon in here? I surely should, yeah. Yeah, that's the problem with using the maps to symbol and the equals symbol. It's very tempting to get confused there. So that's exactly right. So the Ward identity is what connects these two actions. This is the obvious action that the one that has to be that way because that's how the symmetry acts, just by definition, the definition of the symmetry. And this is the non-obvious action, like is there some operator acting on Hilbert space that when you commute it with all observables gives you exactly this observable here when expanded to order epsilon. So this is the non-obvious part. But this thing here, these generators, epsilon, maybe I'll just write it as epsilon mu subscript p mu, those generators there, they carry all the quantum information about the symmetries. Once you know those generators, then you can write down any translation that you like. You can translate as a unitary transformation. You can translate in any direction you want for as much as you like. And that's why we want to, this part is just the definition of the symmetries. These are the things we wish to discover, and the ward identities give us a method to discover these things. So I'll just review the ward identities that we've discovered for conformal transformations in the previous lecture. And then our task today is to specialize to 2 dimensions. And there it's very convenient to use complex coordinates. So part of this discussion so far, we don't always express the ward identities in these forms. Sometimes we simplify things a bit, or sometimes we rewrite them a little bit. This is the case here. Okay, that's the ward identity for translations. So you can regard this as just telling us what is the generator of translations. The generator of translations is the energy momentum tensor. That's all this expression is telling us. Then the ward identity for rotations. This form, which you can also argue. And the ward identity for dilations is this form here. Okay, that's what we had at the end of the last lecture. So these are the 3 ward identities associated to those conformal symmetries. Now, the energy momentum tensor is traceless with respect to correlation functions where there are no fields, which is not mysterious. It's just saying that the energy momentum tensor has 0 vacuum expectation value. The trace. So it's not so mysterious. Even the square of it has 0 expectation value with respect to the ground state. It's not okay. It's not so trivial to prove the statement I'm about to say, but it's true. You take the energy momentum tensor at location 0 and some other location that's also 0, but the energy momentum the trace of the energy momentum tensor is not itself 0 quantumly. This just tells us that this has got 0 component on the ground state. So this is a super confusing thing that people write. They say, you'll often see sentences like this: the energy momentum tensor is traceless. Well, it certainly isn't. It's not traceless as an operator. This operator isn't identically 0. This operator is 0 in these kinds of expectation values, but it is manifestly not 0 in expectations like that. But I'll just rub this from the board. Good. So that's the ward identities associated to conformal symmetries. Now our task today is just to specialize Yeah, good question. Shouldn't this be T mu of x in all the expectation values? Yes, absolutely right. So this is x here, x here, x here. Good. So today's job is to just take these. All we're going to do today is repackage these things in a different coordinate system. So it'll turn out to be a useful thing to do. Often changes of representation lead to the biggest insights. It's like a change of perspective, right? We're going to work in complex coordinates because things turn out to be especially nice when you work in complex coordinates. So we're working in 2 Euclidean dimensions. The line element is just dx squared plus dy squared. But if you express things in complex coordinates, then the line element becomes dz bar, where z is x plus iy. And that means you can write the metric we're going to use a not optimal notation, but it's a notation that we're going to be pretty much stuck with in this literature. So I'm not super happy with this notation. I'll do it this way. I'll do it this way. So the line element, when you express it in terms of these complex coordinates, has this particular expression, and I'm missing one more term, which is just the z bar term, like so. So that immediately tells us what the components of the metric tensor are in these complex coordinates. Right? So if you looked at the symplectic geometry videos, you should be fairly familiar with this. We're complexifying Euclidean space here, and tangent space is also being complexified. But we can be far more pedestrian about this and just define these symbols as just new coordinate system. So the metric tensor in these complex coordinates, well, g subscript zz is 0, is g zz bar, z bar, those are both 0, right? There's no component on either of those directions. But g z z bar equals g z bar z equals a half. So that's what the metric tensor looks like in these complex coordinates. What about vector quantities? Well, suppose we have some vector f vectors are elements of tangent space. And if you want to write f in terms of these complex z and z bars here, then you can do that. You can just use the rule for changing partial derivatives, chain rule, to write f like so. And these fz and z bars can be related to their original components. Like so. And then we also have to worry about tensor quantities. What does a tensor look like in these new coordinate systems? You get quickly used to doing these kind of transformations. So suppose we have something that looks like t mu nu dx mu dx nu, like the energy momentum tensor, for example. Stress energy tensor, what does that look like in terms of what does it look like in terms of z's and z bars? Well, we can just substitute for z and z bar, work out the components of t, and I'll write them out. It's not entirely obvious what you're going to get, but you get used to it, as I said. So the zz component of the stress energy tensor has this peculiar form. It's equal to a quarter Txx minus Ti Tyx minus Tyy, and T z bar is equal to a quarter Txx. That's what the ZZ and the Z bar components are. We also have ZZ bar components. That's for symmetric tensors T. So hopefully with these handful of identities in hand, you won't be so shocked by what I'm about to write down for the ward identities, these ones here. So we're going to take those 3 ward identities that I wrote out before and just change coordinates using these rules, and we'll get the ward identities but in different coordinates. Not particularly challenging, thankfully, but it is tedious. So I don't know a quick, clever way to do this, except sort of component by component. And yeah, unfortunately, that's the only way I know how to do it. So here they come. They're going to look pretty strange at first sight compared to the ones you've just seen before. Okay, that's half of the first one. I've written out turns out that when you write out the first ward identity, you end up with 2 separate equations. And then the second part of the first ward identity looks like the following, slightly different. If you like, we're writing out the real and the holomorphic and anti-holomorphic components of the first ward identity. So that first ward identity becomes 2 ward identities. I1 is this one, I2 is this one, if you like. And you might wonder where the delta function has gone. I'll explain that in a second. Then the next ward identity, that's the one to do with rotations. That one's pretty simple. Rotations are fairly simple in 2 dimensions. You've only got, it's a abelian group. You can just rotate by an angle. Oh, sorry, it's dilations. I've done it in the wrong order. So this is ward identity 2 here. Becomes that. Yeah.
I think you miswrite some expectation about the energy momentum tensor because they're not very symmetric.
So the question is, did I miswrite something to do with the energy momentum tensor because they're not symmetric? I mean, I think I did miswrite something. Z bar Z, Z Z, Z bar. Oh, that's Z Z bar. Sorry. I did miswrite it. Thank you. All right, to actually do this trick, we've used an identity for the delta function in complex coordinates. So I haven't used it for all the delta functions, just for these two here at the moment. So maybe I'll sketch how that's proved. Probably not familiar. Just realized I should have put some underlines on some of the x's. There it's all fine on this side, but here these are two-dimensional coordinates. And I didn't tell you what w was. So wj is the xj plus iyj. So yeah, I guess I better make a comment on how on Earth this delta function thing looks like this thing here. So it's a Gauss theorem argument. Suppose you have the total, you have a integral over space, 2 dimensions, of the divergence of some vector field quantity. So here's x, y. We have some region M. So Gauss's theorem tells us how to evaluate such integrals. So if you've got the integral of a divergence, then that's equal to the boundary integral of the vector field itself. Right. So that's something that no doubt seen in various forms. And what we're going to do is just express this in complex coordinates. Like this is in xy coordinates for the moment. It's perfectly ordinary Gauss's theorem, nothing tricky going on there. So if we go down now to expressing this in complex coordinates, then we find a somewhat interesting version of this theorem. So all I do in going from this line down to this line is just re-express everything in complex coordinates. And we find that it equals that. So it's a little exercise for you to do. Hopefully it's not so difficult given the rules that I've already given you. And then if you look at the expression that we have here for the delta function, then using Gauss's theorem, you can see how to actually apply this in practice. So if you have some other function f, then you can substitute for this form here, and then integrate by parts, and then use Gauss's theorem, and you'll have a residue. So I'll just list the steps. I'll leave them all as an exercise. It's not particularly complicated. So and then the residue calculus will pull off the value of f at 0. So you'll get that answer there. So wherever we, in 2 dimensions, wherever we have a delta function, we're now going to just use this convenient holomorphic, anti-holomorphic description of the delta function. Now we can actually use, I mean, this is a fairly lengthy expression of the Ward identities, right? There's sort of 4 equations you have to remember, and you know, in the current form, I wouldn't say they're particularly attractive nor beautiful. Yeah, question?
Yeah. Why don't you use this identity you show in the 2 and 3 formula? Because there's a data distribution.
That's a good question. Why didn't I, the question is, why didn't I use this delta function identity in this formula? Because I don't think we need it, I think, for what we're about to do. Yeah, in a sense, it's going to be an intermediate step, and then they won't play a role, those 2 equations, beyond setting some components of the energy momentum tensor to 0. I mean, you can substitute it if you want, we just won't use it. Or will we? Yeah, okay, we do, yeah. I can see actually that we are going to use that expression in these final 2 there, but I didn't do it. Whoops, no, I don't want to delete that just yet. So I don't recommend remembering the Ward identities in the form, the intermediate form that I just erased, because we're going to be able to capture all of the Ward identities into one compact expression. It'll be far more useful. So the thing to do is just to add and subtract those last two ward identities and then substitute them into the first ones. Turns out that's a far more convenient thing to do. And then we use the fact that, if you remember back to how correlation functions behave and to the representations of the conformal group, we had these symbols H and H bar, and they are expressed in terms of delta and S as follows. And so when you do that, when you add and subtract those equations and then substitute them into 1 and 2, then you end up with some very nice compact expression for the ward identities. Namely, that this combination here is holomorphic, so it has no dependence on Z bar. And also the same expression there, but with bars. Is anti-holomorphic. And we've introduced some notation here. So this. So this is, essentially this one line here captures the whole ward identities into one expression. It says that this thing here is holomorphic, it doesn't depend on Z bar. In particular, it also tells us that it's got these singularities here when Z is Wj and no higher order singularities. And that means if you take away this partial derivative with respect to Z bar here, if you take it away, then you learn that whatever is in here is some regular function of Z. So there's a similar expression for this equation down here. Oh, I missed a bar. Yeah.
What is T of Z? It's not just T of Z and Z bar is T of Z.
What's this thing here? Okay, that's exactly this thing. Oh, yeah, sorry. Yeah. Firstly, I should have hats on these things. Okay, it's the first thing that's unclear about this notation. The second thing is that this is T of Z, Z bar in here. They really are the same things, but because it's holomorphic, I can just get rid of the Z bar. All right, so far what we've achieved is a lot of index manipulation to rewrite our ward identities into something that's arguably a bit sort of more compact. We've also achieved some insights into the structure of the ward identities. We realize that when we express things in terms of holomorphic and anti-holomorphic parts, that they factorize like this into telling us that the energy momentum tensor is depending holomorphically on Z, the remaining components of the energy momentum tensor.
Sorry?
Yep.
We are missing out these parts where T has in the index Z bar.
We are missing out, that's a good question. Where did the parts with T, Z, Z bar go? They're zero.
Yeah.
They're zero, well, they're not zero for the reasons that I said, because T, Z, Z bar is equal to the trace of the energy momentum tensor, right? That's one of the formulae I wrote. May even still be on the board somewhere. Yeah, there it is. Look at T, Z, Z bar. That's the trace of the stress energy tensor. Right? That's not exactly equal to zero as an operator, but it's equal to zero unless it coincides with a field operator inside this correlation function, and where it gives us a delta function. But that information, we've used that information in substituting those two equations into these equations there. So we haven't lost that information. And so what you're left with is like, this is not directly zero, but there's no more information left that we need to worry about with this function here because we've put it inside these ones here. All right, so far all we've achieved is a reformulation of identities that we knew to be true. We haven't learnt anything interesting yet about T, the generator of conformal transformations. So remember, I started this lecture off by describing there's two ways to do a symmetry transformation. You can use the definition of the symmetry, be it dilation, translation, rotation, or you could posit the existence of a Hermitian generator that does an infinitesimal version of that transformation. We haven't yet learned what is the infinitesimal generator, T hat of Z. We've learned that T hat of Z is more or less all you need to know to be able to do a conformal symmetry, but we don't yet have like a formula for T hat of Z. And for that, we need to take recourse to some quantization scheme. And the quantization scheme that we're going to use is the path integral quantization. That's how we discussed it in the previous lectures. And then we'll find a way to attach, to infer a formula for the generator of conformal transformations. So I guess just one step before we go to that, I'm going to rewrite the ward identity one more time in a way that makes it play nicer with contour integration. So if we do a conformal transformation, x goes to x plus epsilon, an infinitesimal conformal transformation, then we can capture all the ward identities as follows. So this is not entirely trivial that you can get all the ward identities from this expression. I'll just give you the hints for how that works. Remember, if you do an infinitesimal conformal transformation, this epsilon isn't an arbitrary epsilon, it obeys some equations. That's what we covered in the first lectures. So you have to do a bunch of steps before you can convince yourself that actually this is the left and right hand sides of the ward identities compressed together. So now use Gauss's theorem, because we've got something that's the integral over two-dimensional region of the divergence of something. And we covered that. Yep.
But I'm not sure if the first equation of your facts is right. Because you sum over row.
We sum over row here, we have an eta mu nu here,
Yeah.
and we have a mu nu here on this side.
Yeah, but you don't, if you sum over it, you have the first derivative of epsilon 1 plus the first derivative of, the second derivative of epsilon 2. And
Yes.
that's not the same as that.
No, of course they're not the same. No. So, yeah, the question is, why is that the same as that? They're not the same in general, but for conformal, infinitesimal conformal transformations, this is a true statement. So if you remember way back to the first lecture, then we had a condition for a transformation to be infinitesimal conformal, and that condition in general is this. 2 on D, div E, eta mu nu. So if you remember that equation, that's the constraint that epsilon has to satisfy to be conformal. And you can translate that constraint in the case of 2 dimensions into this expression here. And, well, I mean, the first one is obviously that one, and the second one is also a consequence. Have I missed a bar in that second expectation value? Certainly looks that way, doesn't it?
Just doesn't look symmetric, so.
I think I probably have. I just wanted to check before I recklessly correct something. Yeah, I'm certain actually. Z bar. Yeah, pretty certain that's a mistake. So this thing on the right hand, top right, is the integrated form of the Ward identity that we looked before, which was the unintegrated form. And by suitable choices of this epsilon, you know, the generator of translations is a constant epsilon. The generator of dilations is lambda times x. Generator of rotations is x. You can pull out all the Ward identities from this integrated form up there. So this is as far as we're going to get. You know, we can push and pull around constraints to learn consequences, but we're never going to construct anything until we construct something. So that's what we're going to do now. So if we had a conformal field theory, then its correlation functions would obey these constraints here, these integrated ward identities. We still don't have one, right? We're still just pushing around constraints from symmetries. But now we're actually going to exploit the path integral to give us expressions for these correlation functions. So the answer that we're going to use is path integrals in Euclidean space will give us these correlation function expressions. Now, if you take your favorite Lorentz invariant theory and you substitute t equals I tau, then you write down correlation functions like this. Now, whenever you have a correlation function that depends on space-time coordinates, then you can rewrite it in terms of operators at the same time, but with the time dependence put in terms of a unitary between these operators. So it's probably quicker just to write it than it is to say it. There you go. That's what happens when you pull out the time dependence in the Heisenberg picture. So an operator at x time t is the same as the operator at x comma 0, but then you have to conjugate it by the unitary that translates in time. But because we're doing Euclidean time, we're doing everything in Euclidean space, we've substituted t is the imaginary number I times tau. Tau is now our Euclidean coordinate. Now, I didn't cover this in the advanced quantum field theory course, but if you do a path integral in imaginary time, then you precisely end up with quantities such as this. Oh, I should have said that Tj is bigger than, tau j is bigger than tau j minus 1. Otherwise, this doesn't make sense. So if you do a path integral in imaginary time, if you slice up e to the minus h tau many, many times, do the path integral, then you will get an expression for exactly this quantity here. So this will become So substituting for these A's here, I've left them kind of general, but if you now specialize to a field theory, you could say that AJ is that phi j is just A j xj at 0. Oh, sorry. Tau j. And then you have a way to compute correlation functions in Euclidean space like this. Now notice that the I has gone in up here. So the usual path integral formula, the one that we saw in advanced quantum field theory, was there was an I here. But now by substituting t equals I tau, we get a minus s times this here. And we can see immediately that this quantity, subject to some mild conditions, is invariant under the Euclidean symmetries, Euclidean symmetry group. That's, I mean, you have to substitute for an action to believe that statement. And there's one thing to comment on, well, two, okay. Let's convince ourselves that this thing here is sort of rotation invariant, that it reflects the geometry of Euclidean space. So if we took, for example, the action for the Klein-Gordon field, the massless Klein-Gordon field, then we should be able to convince ourselves that this thing up here is invariant under rotations and not boosts anymore in imaginary time. Let's see if that's the case. Okay, so there's a minus here and a plus here, right? Difference of signs here. But if we substitute t equals I tau, then, and this is just not rotation invariant, right? This is invariant under boosts. It's not rotation invariant. Then you pick up an I and an I here, giving you a minus sign, and so you actually end up with d tau phi plus a half dx phi dx phi. So that is actually invariant under rotations. So the Lagrange density is invariant under rotations here. The action, which is the integral of Lagrange density over space-time, is invariant under rotations. The measure is invariant under rotations. You have to convince yourself. You don't get anything anomalous there. And the thing on the bottom is invariant under rotation. So the whole thing on the right-hand side is beautifully rotation invariant. it reflects the symmetries of Euclidean space and not of Minkowski space anymore after you've done this tau, t equals I tau substitution. Thus, we have a procedure for constructing correlation functions which are rotation invariant. But these rotations aren't implemented unitarily, right? We're in Euclidean space now, and translating in time becomes a dissipative operation. It's cooling the temperature, if you like, to translate in time. That's what that expression here is doing. So the price we pay for working in Euclidean space is we make our symmetry group now the Euclidean symmetries instead of the Minkowski symmetries, but those symmetries are no longer implemented unitarily, they're implemented in this peculiar way here. And we're still working, I mean, our original intent is to work with a conformally invariant quantum field theory in Minkowski space, and we are somehow doing that still, right, when we work with this expression here. If we later on substitute tau is minus IT, then we should get back a nice unitary representation of the conformal group. So that's how we will work. It's a nice device to work with this Euclidean path integral. It's no longer unitary here. And we're going to exploit the Ward identities handed to us by this path integral to find an expression for the generator of conformal transformations. But that, I'm afraid, is something that we can't cover today. I'll just make one comment. This constraint here that these taus are always in increasing order, that constraint is respected by the path integral because the path integral always gives you time-ordered results, right? So the path integral never gives you a correlation function where tau1 is coming before tau2. So the path integral keeps things well behaved, and that's why we can restrict ourselves attention to correlations like this. As it turns out, when you have Euclidean symmetries, you can say what time and space are in a much more flexible way. That's something we're going to do in the next lecture. And that will allow us to, instead of writing things in terms of space and time, we're going to choose a completely different variable, what we could call time, and that's called radial quantization. But that, I'm afraid, is a topic for the next lecture. So, for now, that's it. Thank you.